Hello and welcome back. Today we will be discussing few problems related to second law of thermodynamics. So let's begin the problems. A coal burning steam power plant produces a net power of 300 megawatt with an overall thermal efficiency of 32%. The actual gravimetric air fuel ratio in the furnace is calculated to be 12 kg of air per kg of fuel. The heating value of coal is 28,000 kilojoule per kg. We have to determine the amount of coal consumed during a 24-hour period and the rate of air flowing through the furnace. So the efficiency of a furnace is given as work output divided by the heat which is given as input. So from here we can calculate the heat given as input per unit time. This is equal to net work output, which is 300 megawatt, divided by the efficiency, which is 0.32. So the rate of heat input is 937.5 megawatt. From this rate we can calculate the amount of heat input given to the power plant. So this is equal to Q in dot multiplied by time, that is delta T. So 937.5 multiplied by time is, we have to calculate in 24-hour period, so it is 24 into 3600. So this is equal to 8.1 into 10 to power 7 megajoules. We know the heating value of the coal. From this we can calculate the amount of coal consumed. So the mass of coal would be heat which is given as input and the heating value of coal, so which is QHV. So 8.1 into 10 to power 7 megajoules divided by heating value of coal is 28,000 kilojoules, so it can be written as 28 megajoule per kg. This is equal to 2.893 10 to the power 6 kg. From this we can also calculate the rate of coal which should be given as input by dividing the mass of the coal by time. So this is rate of coal which should be given as input is mass of coal divided by time. So this is 2.893 into 10 to the power 6 kg divided by time, which is 24 hours. So 24 into 3600 seconds. So it is equal to 33.48 kg per second. In the second part we need to calculate the rate of air flowing through the furnace. So as we know, the air fuel ratio is 12 kg air per kg of fuel, as it is given in the question. So this air fuel ratio is equal to mass flow rate of air divided by mass flow rate of coal. From this we can calculate the mass flow rate of air or rate of air flowing through the furnace. So m dot air is equal to air fuel ratio multiplied by m dot coal. So this we have already calculated in the previous part. So this is equal to 12 multiplied by 33.48, which is equal to 401.8 kg per second. Moving on to the next question. In this, a refrigerant 134A enters the evaporator coil. So this is an evaporator. Refrigerant enters the evaporator coil placed at the back of the freezer section of a household refrigerator at 100 kilopascal. So it is entering at 100 kilopascal with a quality of 0.2, that is 20%, and leaves at 100 kilopascal and minus 26 degrees Celsius. From here it is leaving at 100 kilopascal and minus 26 degrees Celsius. If the compressor consumes 600 watt of power, so this is the compressor and it consumes 600 watt of power, and the COP of the refrigerator is 1.2. For this refrigerator the COP is 1.2. Determine the mass flow rate of refrigerant and the rate of heat rejected to the kitchen air. COP of refrigerator is the amount of heat which is removed from the refrigerator divided by the work which is given as input to remove that heat. So from here QL is equal to COP, that is 1.2, multiplied by work input which is 600 watt. So QL dot is equal to 0.72 kilowatt. Now if we apply energy balance, so refrigerant is entering from here, some of heat is added, it takes some of heat and then it comes out of the evaporator. So and the energy balance will be mR, this is mass of the refrigerant which is entering the evaporator, multiplied by its enthalpy. So this point we take as 1 and here it is 2. So mR into enthalpy at the point 1 plus QL, which is the heat it is removing, is equal to mass flow rate of the refrigerant and it is multiplied by H2, enthalpy, when it is leaving the evaporator. So this gives mass of the refrigerant or mass flow rate of the refrigerant as QL dot divided by H2 minus H1. Now we need to know H2 and H1. So for H1, P1 is 100 kilopascal and X is 0.2. It is a mixture of liquid and vapor. So H1 will be HF plus X1 HFG at the conditions of 1. So if we see from the steam table of saturated refrigerant at 100 kilopascal, HF is 17.28 and HFG is 217.16. So value of H1 will be 17.28 HF plus X1 is 0.2 multiplied by HFG 217.16. So this is equal to 60.71 kilojoule per kg. Similarly, for second state, it is superheated refrigerant. It is at 100 kilopascal and temperature is minus 26 degrees Celsius. So for getting the value of H, we need to interpolate between these two, as saturation temperature is minus 26.37 and we need to know the values as at minus 26 degrees Celsius. So from here the H2 is, after interpolation, 234.74 kilojoule per kg. So mass of refrigerant will be obtained from the previous equation by putting all the values. H2 minus H1, so this is equal to 0.00414 kg per second. The second part is we have to calculate the rate of heat rejected to the kitchen air. So if we apply energy balance, over the refrigerator, so heat which is given out or rejected from the refrigerator or its rate is equal to the rate of heat removed from the refrigerated space plus power which is given as input. So we know all the values except QH dot. So 0.72 plus 0.60, this is equal to 1.32 kilowatt. So this much amount of heat is rejected to the kitchen air. In the next question, a Carnot heat engine receives heat from a reservoir at 900 degrees Celsius at a rate of 800 kilojoule per minute and rejects the waste heat to the ambient air at 27 degrees Celsius. The entire work output of the heat engine is used to drive a refrigerator that removes heat from the refrigerated space at -5 degrees Celsius and transfers it to the same ambient air at 27 degrees Celsius. Determine the maximum rate of heat removal from the refrigerated space and the total rate of heat rejection to the ambient air. So in this question, there is a heat engine which receives heat from a reservoir at 900 degrees Celsius. So this is at 900 degrees Celsius and at a rate of 800 kilojoule per minute and rejects the waste heat to the ambient air at 27 degrees Celsius. The entire work output, so some work is being produced and this work output of the heat engine is used to drive a refrigerator. So this work output is given as input to a refrigerator that removes heat from the refrigerated space. So this removes heat from the refrigerated space which is maintained at -5 degrees Celsius and transfers it to the same ambient. So it transfers it to same ambient air which is at 27 degrees Celsius. So this is the overall schematic diagram of what is said in the question. Now we have to determine the maximum rate of heat removal from the refrigerated space. So assuming that all the process operates steadily, for heat engine, maximum thermal efficiency is equal to 1 minus TL by TH. So for heat engine, TL is 27 degrees Celsius and TH is 900 degrees Celsius. So this will be 1 minus 300 divided by 1173. So it comes out to be 0.744. So this is the Carnot efficiency of the heat engine. Writing this in terms of work and heat, so work net output, this is the work output divided by QH. So this is QH for heat engine, Q dot H for heat engine. From this we will get work output from the heat engine and this is equal to efficiency 0.744 multiplied by QH dot for heat engine, that is 800. So this is equal to 595.2 kilojoule per minute. Now this work is given as input to the refrigerator. The rate of heat removal from the refrigerated space will be maximum if the Carnot refrigerator is used. The COP of refrigerator is TL divided by TH minus TL and this is equal to, for a refrigerator it will be 273 minus 5 divided by is 300 minus 273 minus 5. So this is equal to 8.375. Marking all the notations. So here the heat which heat engine is taking from a source at 900 degrees Celsius, it is Q dot H of heat engine. It is rejecting heat to the ambient air which is QL dot of heat engine. For refrigerator it is taking heat at -5 degrees Celsius. So this is marked as QL dot for refrigerator and it is rejecting to the ambient air which is marked as QH dot of refrigerator, and the work is work net, which is given out from the heat engine and is taken as input by the refrigerator. The rate of heat removal from the refrigerated space becomes QL dot R is equal to COP of the refrigerator multiplied by net input work, and this is equal to 8.37 multiplied by 595.2 kilojoule per minute. So this value comes out to be 4982 kilojoule per minute. Second, we need to calculate total rate of heat rejection to the ambient air. So from both heat engine and refrigerator, some heat is being rejected to the ambient air. So from the heat engine, QL dot of heat engine is QH dot minus net work, which is given as output. This is equal to 800 minus 595.2. So this comes out to be 204.8 kilojoule per minute. And from refrigerator, QH dot R is equal to QL dot plus work, which is given as input. So this is equal to 4982 plus 595.2. So this is equal to 5577.2 kilojoule per minute. So total amount will be sum of these two. So this is equal to heat engine plus QH dot of refrigerator, and this is equal to 204.8 plus 5577.2. So this is equal to 5782 kilojoule per minute. So this is the amount of heat which is rejected to the ambient air. In the next question, a household refrigerator that has a power input of 450 watt and a COP of 2.5 is to cool 5 water lemons 10 kg each to 8 degrees Celsius. If the watermelons are initially at 20 degrees Celsius, determine how long it will take for the refrigerator to cool them. The watermelons can be treated as water whose specific heat is 4.2 kilojoule per kg degree Celsius. And after that, we also need to explain, is our answer realistic or optimistic. For a refrigerator, it takes some heat from a space maintained at low temperature and it gives it to a space at high temperature, and some work is given as input. So it is given in the question, power input is 450 watt. Now COP is given, which is 2.5. We can calculate the total amount of heat which needs to be removed to cool the watermelon. So that heat which is to be removed is QL, and that is equal to MC multiplied by delta T for watermelons. And this is equal to, there are 5 watermelons, so for each multiplied by mass of each is 10 kg. Specific heat is 4.2 kilojoule per kg degree Celsius, and the temperature difference is, it is cooled from 20 to 8 degrees Celsius, so 20 minus 8. So this QL is equal to 2520 kilojoule. So this is the amount of heat which needs to be removed, total amount. and the rate of heat removal from the refrigerator is QL dot, which is equal to COP of the refrigerator multiplied by the rate of work which is given as input. So this becomes equal to 2.5 multiplied by 0.45 kilowatt. So rate of heat removal from the refrigerator is 1.125 kilowatt. So from this we can calculate the time needed to remove this QL amount of heat. So time will be total heat which is to be removed and the rate of heat removal. So 2520 divided by 1.125, this is in kilojoules and this is kilojoule per second. So it gives 2240 second or 37.3 minutes. And this answer is optimistic since the refrigerator space will gain some heat during the process from the surrounding air, which will increase the workload. Thus in reality it will take longer to cool the watermelons. So we will end this lecture. Thank you.